Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on March 2nd, 2026, just 2 days ago. It presents a new mathematical framework for tensor layouts that allowed researchers to replace 55,000 lines of complex library code with just 3,000 lines of core representation. The paper is titled CuTe Layout Representation and Algebra, and as we'll see later, the implications for writing high-performance GPU kernels are really significant. To see why this matters, Figure 1 illustrates a core limitation of traditional data handling. At the top, we see the physical data arranged as a simple linear sequence. The table below compares different ways to view this memory. While the first two rows work fine with standard flat strides, the third row presents a problem. Here, creating a 2x4 matrix view causes the flat representation to fail, marked by the red cross, because the memory jumps are too complex for a single integer. In contrast, the CuTe representation on the right handles this effortlessly by using nested, hierarchical strides. So, Figure 2 details how these coordinate systems map indices to shapes. On the far left, a basic shape of size 4 just uses linear integers. In the middle, a 2x3 shape uses coordinate pairs, ordered so the first number changes fastest, which is known as lexicographical order. The most important example is on the right, showing a nested shape. Instead of a flat list of numbers, the first dimension is itself a pair, creating a hierarchy. This structure is what allows the library to verify complex GPU tiling patterns at compile time. Well, Figure 3 translates those abstract shapes into concrete memory patterns. The top row displays standard layouts like column major and row major, along with a padded version, which traditional libraries handle easily. However, the bottom row demonstrates the unique power of hierarchical strides. Panel E represents a mixed layout that forms a grid of tiles, a structure critical for GPU tensor cores because it matches hardware expectations. Finally, Panel F illustrates a blocked broadcast, where setting strides to 0 repeats values logically without duplicating them in memory. Alright, moving from the visual to the mathematical, Table 1 shows how CuTe treats every layout as a linear transformation. The top row displays the standard case, where integer strides form a simple one-row matrix that maps indices to memory offsets. Below that, the middle row expands this to coordinate strides, using a multi-row matrix to map indices into multi-dimensional logical spaces. Finally, the bottom row introduces binary strides using the F2 field, where matrix operations become XORs. This capability is crucial because it allows the system to represent complex bit swizzling patterns, which are often required to avoid memory bank conflicts on GPUs. So, Figure 6 applies those mathematical concepts to a concrete hardware requirement. This grid visualizes the specific thread value partitioning for an 8x8 matrix on an NVIDIA Ampere FP64 tensor core. Each cell displays a T label for the thread ID and a versus label for the value index, indicating exactly which thread processes which data element. Notice that the pattern is not linear. For example, thread 0, marked T0, handles adjacent values in the first two columns, while other threads fill the rest of the row in a swizzled arrangement. This layout is hard-coded into the silicon, so the library uses the algebraic framework to ensure software data patterns match this physical reality exactly. Following up on that hardware pattern, Table 4 demonstrates how the layout algebra adapts it to different memory formats. The middle column fixes the exact Ampere tensor core pattern we just saw, labeled as T versus layout B. The left column then varies the physical storage of the source data, ranging from standard column major arrays to complex interleaved or swizzled structures. By composing these two, the rightmost column derives the precise addressing logic needed for each case. This ensures that a single kernel can support any input layout, because the algebra automatically handles the complex index math at compile time. Well, Figure 7 visualizes a powerful feature called tilers, which use layout composition to slice data. Here we see 4 examples of extracting a 4x8 submatrix from a larger 8x16 layout. Panel A on the far left shows the standard contiguous slice, just grabbing the top left corner. But looking at panel B and D, the algebra allows for much more complex extractions. Panel B takes rows in a specific strided pattern, while panel D selects every second element in both dimensions to create a sparse view. Because these are all just layouts, the compiler optimizes the addressing math automatically. Wrapping up, 2 takeaways stand out. First, Treating data layouts as composable algebra rather than hard-coded indexing logic drastically simplifies high-performance kernel development, shrinking 55,000 lines of library code down to just 3,000. Second, this abstraction is critical for modern deep learning, serving as the mathematical backbone for cutting-edge systems like Flash Attention and NVIDIA's Cutlass library. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.